painting faces using generative adversarial networks. And I'm trying to solve like similar problem to the other group that's making the floor plans. Like we want to reconstruct a missing area of an image, and I'm trying to do that using DC GANs. And so I want to give like a brief overview of what generative adversarial networks are. So there's a generator that starts with a random probability distribution, and it tries to generate samples that reflect the original distribution. And at the same time, there's a discriminator that detects whether the data is coming from either the generator or the original distribution. And a good way of kind of like thinking about this concept is imagining it as like counterfeiters and police. So the generator is kind of like a counterfeiter who tries to make their fakes as good as possible, and the discriminator is like the police that tries their best to detect all the fakes and weed them out basically. And so it's kind of like the movie Catch Me If You Can. Like both of them are working to like solve each other's problems and helping each other like reach a convergence basically. And so I want to see if using these networks I can perform in-painting on images from original dataset, and also like make another dataset conform to it. So I kind of got like inspiration from Priyanka's project using cleft lips. Like I want to see if I could take out a portion of the mouth of like a person with a cleft lip and see if I can try to recreate their mouth with like put together without the opening on the lip. And so yeah, I'll go into that some more. So just like a brief overview of some of the related work, unsupervised representation learning with DC GANs. So this is a paper that kind of describes how the DC GAN model works, and they go over like striated convolutions and vector arithmetic for images. So for striated convolutions, it kind of like upsamples using the DC GAN, you get like a vector representation of the image that you want to generate, and it kind of upsamples it so that it can produce the full image later. And for vector arithmetic, they did like cool stuff like subtracting glasses and like turning into women. So man with glasses, man without glasses, woman without glasses, it turns into a woman with glasses. So there's cool stuff like that. And the paper that I'm basing most of my work on is this paper, Semantic In-Painting with Perceptual and Contextual Loss. So it uses a DC GAN with two different loss functions, and the first one is a contextual loss that tries to see how similar the generated image that you're using to in-paint the missing part is to the original image that you're trying to in-paint, and also a perceptual loss, which tries to make sure the generated image that you're using is as close to original distribution as possible. So using those two things, it does a pretty good job of in-painting some of the images. And I also looked into another paper that did in-painting with context encoders. So they use kind of like a encoder-decoder framework, and they use pretty similar functions, loss functions, as a semantic in-painting paper with DC GANs, and it's basically like a contextual and reconstruction loss too, but they just name it something else. And the cool thing about this is it was able to learn features from the images automatically. So like after it trained the encoder-decoder framework on a bunch of images, they were able to learn like the spot, like basically the middle of the image that was missing, and do like different types of classification on images. So I thought that was pretty cool. Going into the approach that I took to do the in-painting, so I wanted to train a DC GAN on a data set of celebrity images, and then basically it kind of plays like this mini-max game where the discriminator is trying to like basically find all the bad generated images, and also like the generator is trying to get as many of the images past the discriminator as possible. So that's how you see like the 1 minus d gz. I also wanted to do the inpainting and use like this type of formula where you take like a mask of an image, and that basically gives you what parts you want to keep and what parts you want to take out, and using like a contextual loss where you see how well like the missing part fits with matches with the original part, and also like a perceptual loss.
So
that
M is the mask? Or?
Yeah, M is the mask, and basically like the contextual loss kind of checks to see like how well the missing part that you're adding in matches with the other parts around that the mask kept before, and the perceptual loss just checks to see like how well the generated image that you're using would be detected by a discriminator. So whether it could like pass by like the discriminator or not. And like using those two things, I like added the loss function together, and this lambda kind of controls like how much you want to weigh the contextual and perceptual loss with each other, and you just find like the minimum. You take like the gradient and find the minimum after that. So
the mask is like lets the image through when it's 1, or when it's
when it's 1, yeah, and then when it's not 1, then it takes it out. So it keeps like whatever's in here and
right, and takes whatever was not in there and fills it in.
Yeah, for the generated image, they take whatever's not in there and then just like add them
So
together.
the 1 minus M kind of inverts the mask.
Exactly, yeah. So the dataset that I use is a Celeb A dataset, and it has like over 200,000 celebrity face images. And I also took like some random images I found like through Google search for people with cleft lips. And I'm setting it up with a DCGAN that works on 64 by 64 by 3 images. And I pre-process all the images so that it would be aligned with their eyes and lips, just so that it would be like easier to generate the images. And I also use Atom to optimize the learning rate for training. And so my setup, I'm trying to like perform in-painting on 2 different subsets. So I want to reconstruct the celebrity faces, the original celebrity faces that I had, and like take out like a portion of it and try to reconstruct it, and also reconstruct like people with cleft lips and try to fix their lips basically. And I plan on trying to tune on the lambda for the reconstruction and contextual loss to see like how much those factor in, that's probably for later. And right now, I actually just got results from Li Xing. He sent me one of my code proofs, and this is a discriminator and generator loss. It seems like it kind of converges pretty well at this like 10K spot, but then the discriminator gets like a lot better and generator gets a little worse as like time goes on. I'm not really sure what the reason for that is.
Is it possible, so you took someone else's code mostly, right?
Yeah.
Is it possible that they had like a scheduled change of the learning rate? It's in there.
Yeah, I think Atom is just like optimizing it.
Oh yeah, okay.
So it might be doing some weird stuff with that.
That's interesting, but it's not actually that bad. Quite interesting still though. What I think I sent you the Wasserstein gun thing. That should possibly alleviate that issue that the generator gets like funky at the end.
Okay.
Possibly. Do you have some images?
Yeah. So here are like some resulting like sample images just for the generator. It seems pretty good. Like they look kind of like real images. Some of them are kind of wonky, like this one up here. But overall, it seems like the generator was able to create like pretty good samples from the original data set. And also I tried performing the inpainting, and like just on the celebrity images, it seems pretty good. Like this like inpainting is really good. This one is also really good. There's like some of them that are kind of bad, but if you look at the cleftless one, it's not that good. And I kind of suspect that it's because I'm training on like a celebrity data set, so most of the individuals are like older and their faces don't really match like baby faces or child faces that look different. And so I think like in the future I might try to find a child data set to train on to see like if it would basically improve on that. Like the images that it's using for the inpainting I checked the completed ones afterwards, and they don't even look like real faces. Like it had a really hard time finding like a good representation to like match the inpainting with. So hopefully I can find like another data set with just child images, but there's not like as much public data available for that, so it might be kind of hard to do that. But yeah, that's my hope.
Is that baby with teeth?
I have no idea.
Like
I think it just really messed up, so it's kind of like teeth. But yeah, that's basically it.
Okay.
Yeah, that's it.
Great.
Right. Yeah, you might be able to just use Google image search to get a lot more baby images. Possibly you'll need some manual tuning there.
How much do you think I'll need to train it on DC? Like at least 1,000?
Probably. So one of the things you could do is kind of train it on the celebrity faces, and then maybe refine it or like fine tune the model with a separate data set on the baby faces. So you just kind of like train the model until you kind of reach conversions, maybe at the 10,000 level, and then you reduce the learning rate and train it on like a smaller subset.
Okay.
That could be a way to do that.
Okay.
Yeah, and so what else do you plan to use other evaluation strategies?
Yeah, so I was gonna ask you about that too, because I don't really know like a good way to evaluate the inpainting, especially for like the cleft lips. Like it's kind of just human evaluation, since I want to like change how the lips look.
Yeah. I mean, obviously, you could do some human evaluation and inspection. Another way also would be to, and it probably doesn't work on the inpainting with the babies, but might work on the celebrities, and there you could compare, for example,
the loss.
Yeah, the compare like the reconstruction loss between multiple methods, maybe, so that you have some comparison on a.
I mean, I could probably convert them into like image vectors or something, and then compare, because I have the original image too, right? So
right.
Could I just compare like the loss between the two vectors, or like how much it changed? Basically?
Yeah, exactly. Yeah.
Okay.
But then between multiple methods, so that you have like an argument, hey, this method actually works better, or doesn't work better. I mean, one interesting component would be to add the Wasserstein approach to the contextual and perceptual loss DCGAN. That would be an interesting addition to that. And I think it might not be so hard to do. But yeah, well, we could talk about that if you want. Okay. No, I think it's just basically adding, changing the Minimax loss into you're running the generator multiple times, I think, and then you take multiple runs and add that in. So you're treating it not as a one-off, but more of like I want to know the distribution of it, and you approximate it through multiple runs. Okay. But yeah, so we can talk about that. It should be possible to put that in. Okay. Yeah. Cool. Any questions?
I mean, it's not a question, it's just a comment, I guess. I feel like this is something that Operations Smile might be interested in, but if you're willing to go through like 3 months of approvals, they might actually be able to get you like a giant data set. It's just, there's a lot of paperwork involved.
I mean, if you're going through that anyways, I mean, like maybe, so one of the things that I was thinking about is like, I mean, the ideal case for your projects here, for everybody, is that we write a paper about it. And I think if we combine your two efforts and like you had the architecture, which I think is kind of cool, and then other projects as well. So there is a pretty good conference coming up with the submission in September, AAAI, and like if we can have like 1 or 2 papers going there, I'd be super excited about that. So yeah, I think that would be kind of fun too.
I think, at least like with my project, Operations Smile is already in the process of writing several papers as well. So you can also probably like piggyback off, like onto one of them as well, and that'll like save time. But again, I think it's just the approvals, because it took me forever, and I only got like 70 sets.
Yeah, so how many pictures do they have?
They have access to like thousands. They've been doing this for, I don't know, 20 some years at least, maybe longer, I can't remember. It was originally like the current CEO's dad who started it, and he used to tag along when he was a kid. And now he's like board certified plastic surgeon, so that entire time. And then they literally have a plane that they used to do surgeries on, so they fly everywhere.
Oh wow.
Yeah, so they gave me images from like 4 or 5 different like samples of like the cities that they did surgeries in. So they have plenty, and then they also have a lot of like genetic and epigenetic data. And if anyone wants to do like a project down the line, they're just like, we have all this data, we just don't know what to do with it. So if people like start doing their like their HIPAA and all that stuff, all the trainings ahead of time, I mean, they'll give you whatever you need. It's just a matter of like getting cleared. I think that's the biggest challenge there. But they have a lot that they're willing to let students tinker around with.
Yeah, I mean, if you want to put us in contact, that would be really interesting. I think that might be a cool project.
Okay, yeah, I can shoot them an email and put you guys in touch.
That's cool. Awesome. Thanks. Yeah, I think there is something to be done. It's kind of like, I was wondering, yeah, it's like the application, like to see how the face will look like after surgery or something like that. I think that would be kind of interesting.
They also have a lot of like the before and after pictures.
Oh yeah.
So that'll also
That'd be perfect.
helpful, yeah.
Do they have the full faces though, or?
So.
Because I know I asked you before, and you said the ones you had were just the mouth.
It's, yeah, so it depends. Some of them are like cut off like mid-eye, like it varies, but I mean, they're doing these surgeries all the time, so if you just like, and they're very interested in AI, so if you just tell them ahead of time, like whatever their latest mission is, they can just make sure the pictures are whatever, and going forward.
Okay.
Yeah, but it's really interesting what they're doing. And that was really cool that you like pulled in Cleflet or something.
Oh, yeah.
All right. So let's continue. We talked about word embeddings last Wednesday. And I'd like to continue with that. So we talked about the shortcomings of like traditional ways to embed or to encode language. First of all, the problem with language or words is they're symbols and they're not really easy to be treated with like the neural networks and we like numbers more than symbols and continuous numbers at that. So we wanted to find out a way to actually represent words in such a vector space that doesn't have like these super sparse bag of words characteristics and has a couple of more like desirable characteristics. And so, for example, one of the things was that we want to have semantically similar words that end up nearby each other, and that maybe there are actually these clusters of like topics that are being learned, and this base is based off of like the distributional hypothesis, which basically just says that words that are similar will happen in the similar time frames or similar contexts in language, and at that you can, for example, depending on your domain of investigation, you can look at that in any way you want to. So for example, you will learn a different representation space through this distributional hypothesis if you learn these embeddings on, let's say, the Wall Street Journal or Wikipedia or a conversational data set. So you will, it really depends on the context in which you are learning these embeddings or representations. So, for example, in Wikipedia, you could expect some of these things to come out. So, for example, Wikipedia is pretty extensively authored on like stuff like geography or politics, even religion and some other facts will be present in Wikipedia. However, you probably will not be able to find relationships like that in a conversational corpus, because unless you have people talk about their trips, you would not have like countries come up that often, I would imagine. So that's really dependent. But what we want to learn is this embedding where we go from a word representation that's basically just an ID of a word in your vocabulary to a real vector space with n dimensions, and n could be anything but pretty small. Like you don't want to have like a million dimensions in that space anymore. You want to have maybe like 100, 200, 300, something like that. So from now on, then, or like what these embeddings do is they basically transform this word to a real vector in this space. And now we can actually compare these and compare, for example, how close or how similar train and track are from each other. A couple of ways to do this, for example, would be the Euclidean distance. So you want that to be small. Another way to do this, and this kind of more common and more frequent, is the cosine similarity. So basically, you look at how similar the direction of the vector is, and if it is perfectly similar, the cosine similarity is 1, and if it's completely orthogonal to each other, it will be 0. Okay, so we learned these embeddings, and the nice thing about the cosine similarity, obviously, is that it's not like from 0 to infinity. It's from 0 to 1. All right. Great. So while we also observe other properties which are actually kind of great and also desirable within this vector space, is that we not only learn that similar words are close to each other, but we can actually compute operations like Stephen just showed on the man with glasses, man without glasses. You can compute those operations in this space in a similar fashion, where now if you have a man and you subtract the vector for man, if you have woman and you subtract the vector for men, you actually learn a similar distance as, or you observe a similar distance as if you take another word where you know the gender of and the opposite kind of with the other gender. You can learn these like distances between these two words. So man to woman, man to woman is like aunt to uncle, and you would go in a similar direction, even though these words might not be located in a similar space anymore, but the distance or the relative distance to these words might still be the same, and this is actually one way to evaluate how these vector spaces function and what they learn, and this is kind of like the analogical reasoning that is used to evaluate these spaces. Obviously, the analogical reasoning also is kind of like arbitrary in the sense that you can choose the analogies that you want the vector space to represent yourself. And so, for example, if you use this analogy example on a data set that is learned on conversations, your data set or your representations will perform very poorly, right? Because they do not have these representations enough in the data set. So you can only compare these analogies between similar data sets. So that if you compare one method versus another method and you want to see if the method is outperforming the previous state of the art, you will have to use the same underlying data set. You cannot just use a different data set. Does that make sense? So you kind of like learn these topical representations. If you take a conversational data set where individuals talk about like their hobbies, you will not find Berlusconi and Silvio or these kind of relationships in there. Or it's fairly unlikely that you will learn it sufficiently. So that's one of the caveats. However, it's nice that these kind of relationships are being learned as side effects. And I have an example towards the end of today's lecture where I show you that one of the desired side effects that we wanted to have in our data set was that we want to learn like locations of emotional words in such an embedding space rather than these relationships between country and capital and so on. Okay? Alright, so we then talked about a way to actually learn this, and that would be, for example, the maximum likelihood to compute basically a word given a certain context, and so this is like, I want to know the word at time t given, or at location t given a certain context of the word, and the problem here is that we would have to kind of normalize this through every other word, and that's kind of like expensive. So this is not a sufficient, an efficient way to compute this, and so this is kind of like this would be the way to investigate this, where you basically have the context that comes in, and you want to predict which word in your vocabulary and capital V, depending on like whatever like language size you want to investigate, could be very large. So you could have like 100,000 different outputs here if you wanted to learn a language with 100,000 words. And English has more than 100,000 words in the vocabulary. So your problem almost becomes impossible to learn the next word, which is the target word, and is located at WT. And you want this score to be larger than everybody else's score, right? So these are all the other words in your vocabulary. And to compute this, it would take almost forever. So one way to do away with this problem of where you have to learn the contrast between the target word and every other word would be to learn it, learn the contrast between a word and a bunch of garbage words that you don't want to model in this case. And for that purpose, you could choose, let's say, 10 different randomly chosen words. But you can also use 5 randomly chosen words, and you can use 1 word as well. And so this is what is being done to learn these word embeddings, where your loss now basically is trying to detect, or like you try to change the probability you try to have this larger than the expected value of some noise words, and you can make this noise value more and more accurate if you use more and more of these K words here. So you don't just use one, but you use K many, and if you use K as very large, you approximate this problem quite well. But if you use K as a smaller value, you still get close to that, but you don't have to compute that many different probabilities for each of the words. Does that make sense? So it's just kind of like a, we don't have to go into like super details and like how to train this, but just so you know, we train these word-to-vec representations not based off of like a softmax, because it has an output of 100,000 dimensions, and so that would be very difficult to do. And here we kind of like just approximate that with the target word versus a couple of garbage words or noise words, and you can randomly choose those garbage words. And if you choose them unfortunately too close, you'll have trouble again, right? You don't want to compare train here or mat, the cat sits on the mat, with couch, chair, stool, and so on. So that would be very difficult to actually learn a contrast there, but you want to compare that to, I don't know, Timbuktu and stuff like that, okay? All right. There are a couple of different types of ways. So in this case, we are trying to infer the next word based off of what we call the left context. But there are different contexts as well. So for this example data set, the quick brown fox jumped over the lazy dog. The left context of the word brown would be the quick. The right context, fox jumped, and the surrounding window context, so to say, would be quick fox. And this is kind of like how you prepare your data set depending on the type of context that you choose. So do you want to predict the previous word, do you want to predict the next word, and so on. So you kind of like try to learn these like representations based off of these context words. So we would have the surrounding window context for a bunch of the words here, but you can also have the other type of context. So in this case, the skipgram in fact actually tries to invert the task and predict a context from the target word, which is also kind of interesting. So the data set then in this case becomes like a separation between like quick so you want to predict the previous word, and from quick you want to predict brown, and so on. Okay. So and training is again accomplished through this function here, and what we need to do obviously is we need to compute based off of these thetas here, and we need to do the partial derivative again to get at those embeddings, and we're doing like gradient descent again. So this is very similar as we have had that in our previous machine learning examples. I showed you another word embedding. Here is another example which can be looked at. So in this case, for example, we have like computer, system, words, etc. And then we have like single characters up here. There are some numbers, million, 0. He, she, it are down here. Each and every, no, and, another are there. So you kind of see that there are these representations, and I would like to mention this briefly. But t-SNE is a useful way to represent or to display your variables here, and t-SNE is so it's called T, which is a number, stochastic nearest neighbor estimation, which basically is similar to PCA, but is not as like dependent on like sparse representations and so on. So it allows you to basically represent a high-dimensional space in a low-dimensional form, and this is often used for evaluation purposes. So because these, as I mentioned earlier, these word embeddings are often pretty difficult to evaluate if you don't have these analogy vectors or these analogy data sets that you want to compare it with. You're kind of stuck with like a visualization or like your loss overall, how well you're doing to evaluate the model, but then these visualizations help you better understand what your like hidden space kind of looks like. All right. There are other methods or other things that you can actually also learn with these representations. Is, for example, displayed here, where you can actually try to basically learn representations of multiple languages in one single space. So you would, for example, try to fit English and Chinese into the same space, which is, I think, quite interesting to do. And what you would have to do is basically learn word embeddings for English as well as for Mandarin, and then kind of learn a joint kind of representation. You can force these representations to be about similar, and you can then kind of like add them up. So like what are ways to kind of like make these representations similar? Of one, for example, would be to enforce like canonical correlation analysis on each of the dimensions, so that the dimensions are correlated with each other. But yeah, so you can learn this also if you have like a one-to-one translation between the two languages. You could learn these as well jointly. But yeah, so this is just an example of like what else you can do here. You could then use this for translation purposes or for finding analogies in a different language, and so on. So it's kind of like interesting to do. Another thing that you can actually, yeah.
Sorry, but for example, like besides translation, what else, like possibly correlation you can find within different languages?
So if you learn multiple languages, translation is the obvious thing, but then also I would say that you could, for example, like observe differences between languages and like try to see like where the languages coincide or where they like differ from each other. But I'm not really an expert on that, so I'm not sure what else you could use it really for, but let me think. So if you have an embedding space of multiple languages, Yeah, apart from translation, I'm not really sure what else you could use it for. Yeah, I'm not quite, I don't really know. Maybe you have an application in mind.
Yeah, because we, like, I'm actually working on another project that's, like, we want to do some translation work, so I'm wondering, like, beside, like, what is the main principle behind this, like, representation?
So if you want to do machine translation, I'll show you later on today a model that you should probably try out more than than this kind of model. Yeah, those make a lot more sense than this. So in this case, you can find like translation from one word to the other, right?
Mm-hmm.
But what about like generating a sentence actually, right? I think that's a very different task. So you will need to look at sequences rather than just a single observation at one point. Okay. Actually, we're going to go into that in a second. Okay. But then you can also learn other kind of like multimodal representations where you have both words and images kind of live in the same space, which I think is pretty interesting. And we'll also see again another example later on where we can use models to generate basically captions for certain images. And this kind of learns similar representations to that. And this kind of like, it can be used also for retrieval of images so if you have a manifold where both images and words live in, you can type in a word and retrieve all the similar images from that. So that would be kind of like one way to think about this for an application. Again, what we try to do in the multimodal machine learning world is often related to this, where we have in the same space like different values living in, or like different so I guess what I'm trying to say is like this dot here is in the same low dimensional, maybe 100-dimensional space than this plus here, right? But the dot corresponds to a word, and the plus signs correspond to images, right? But if you think about this in kind of like, instead of like a word to vec in a speech to vec kind of idea where both the acoustic signal but also and the verbal information might actually have like a joint relationship with each other. You don't just want to have a voice signal and a word signal close by each other, because then you learn basically the acoustic representation of how to say a word, so you can use that for speech recognition maybe. But you don't really learn that relationship that I mentioned last week, where you can walk from house to house, right? And then you have the acoustic change, and you would change that according to the affect or the emotion in the word. So I think these are neat for retrieval tasks, but if you actually want to try to understand the relationship between both the word and the image in this case, or the word and the voice, I think you need to try to project into each of these locations a pair of them rather than like them separately. So in this case, you have a multimodal space where entities of a single modality kind of live in, but you can imagine this to be joined so that every dot is basically containing information from both modalities at the same time. Alright, so let's continue on to the next topic. In this case, one of the probably most famous models right now, and it was invented quite a while ago, actually in like 1997 by Hochreiter and Schmidhuber, and in this case they tried to solve a problem that a lot of conventional RNNs have, and we talked about this earlier in the class when we unfolded our recurrent neural networks through time, and we had a problem there because we need to compute the error at the output and then backpropagate the error through the network. And one way to do that was to unfold the network in time so that we actually have like a feed-forward neural network, and then backpropagate the error through time through all the layers of this network. The problem there is that we have either, again, a gradient that goes to 0 very quickly, and then the early stages, or the early stages don't actually have any input anymore onto the training, or we have the problem that the gradient explodes, and then we have another issue there. So the idea here was now to kind of change that problem and allow us to learn long-term relationships. We're going to get into that. And the long, however, stands or is situated in front of short-term, right? So it's long, but it's not super long. It's still pretty short. Like, you can't learn sequence dependencies over like thousands of time steps. It's still short-term, but it has kind of like a longer short-term memory than before. So let's look at previous ones. So previously, just general recurrent neural networks, they have some loop. So I have a connection between, so I have an input, I have an output, and then, but I have a connection in this neural network that might be to a neuron itself or to the next layer, and the layer has a connection back, and so on. So there might be these kind of different connections. However, I'm using the current state of the network to feed back into my network, right? So in the beginning, I don't have the current state of the network coming in, so that kind of like is 0 here. You can also, if you want to, you can randomly initialize that state as well, if you want to train it like that. But then we receive an input and we produce an output, okay? And then we have a network state, and the network state is kind of like propagated on for the next time step. We get another input, and then we produce another output, and then we get another input, and we keep our state, we produce another output, and so on. So that kind of like is how these networks, and we had an example where we can unfold them through time, right? And so how these have problems such as vanishing gradient, etc. So they can't really learn very long sequences. So they function for like sequences of like 5, 6, 7 items, but typically they would fail afterwards. So what the LSTM now wants to try is, we want to see if it is possible to basically kind of identify from very early inputs if we can actually influence an output at a very much later stage, right? So one way to think about this could be if you have a very long question and you want to know what the answer is, you would have to like remember all the time steps, and then depending on the first word, which could be like how, what, who, etc., you would know what the answer would be. So you need to know all the context that you learned through the question, what the question is about, but also then you need to know the item that is like queried, right? So you want to know either a person, like you want to know the characteristic of a person, etc. So this could be imagined like that. So you want to kind of have these early inputs still produce kind of like an output at a much later stage. And so in traditional recurrent neural networks, this unfortunately is not really possible. So one way to see or to look at this, why it's not possible, is well, they're not very complex. So they have like this one neural network layer in them, and we talked about this in in an earlier class where basically you have just a normal layer, and in this case we're reducing it to one single neural layer. You can have multiple of those obviously as well. But so you have like one normal MLP layer in there, and the activation function of that layer is a tangent superbolicus in this case, so it's kind of like noted like this. And what we do is we receive an input, and we have the previous state. They both feed into this tangent superbolicus, and you might, so how does that work? Well, we don't compute actually an operation on this, it's just different different weights. So basically, if this is one neuron, it gets input, it produces an output, but then also it has this connection here. So unfortunately, one way to draw that better, I think, would be to show it like this, where where A comes in like this, so that's the previous state, and then the input comes in like this. So they basically are just concatenated. You don't compute an operation on them, right? So basically they just go in next to each other, and there are separate weights for both of them. But then we compute whatever output this guy produces, and then this is the same output that goes out here. So this is what the network spits out, but also that state also goes into the next state of time. Okay, so this is all that happens here, and if you backpropagate through here, you have the same issues as previously. So what do LSTM networks now do differently? Well, quite a bunch. So this is kind of like how complex these guys look like. So there are a couple of things happening in there. So first of all, we have like, and this is the full LSTM. There are simplified versions of those as well, like gated recurrent units and stuff like that. They have a few less of these. But anyways, so there are basically 4 layers now. We have the traditional layer still in here, which is with the tangent superbolicus. So that guy produces from -1 to +1 outputs, okay? So that's important to keep in mind. And these guys here, they are sigmoidal, and they only produce from 0 to 1, okay? And you can already kind of imagine what these guys are supposed to do. Well, one of the things that they're supposed to do is either let stuff through, so they would produce a 1 or something close to a 1, or they cancel stuff out, and then they would produce something close to 0, okay? So they don't themselves kind of like contribute to the computation, they kind of contribute more to like a forgetting or retaining kind of gating functions. So these are gating layers, and this is kind of like the computational layer, okay? And then, and you can see why these are the gating layers, because their output now goes into these like basic operations. In this case, the x is a pointwise multiplication. In this case, the plus is a pointwise addition. Again, a pointwise multiplication, and another pointwise multiplication. And here you just have like kind of like a normalization factor that you want to use, and so that your next step or next output doesn't go like bonkers, so to say. Okay? Alright, so let's go through this step by step. So the first important thing about these LSTMs is that they do have like kind of like one major avenue or artery that goes through here, which basically holds the cell state, holds the information of the cell state, and the cell state of the network flows through time almost without any changes, so it doesn't go through like a sigmoidal layer or a tangent superbolicus layer. It only goes through these pointwise multiplications. Okay, and pointwise multiplications or additions. And so if you think about this cell state like as the memory of the cell now, and you can imagine now with this gate here, through the multiplication here, you can either retain information in the cell state or in the memory, or you can cancel it out, right? And you can do that in a continuous fashion because of the sigmoid here. So what this does here is it gets the previous state of the cell and then decides, do I want it or do I not want it? Or which dimension of this state do I want to retain and which one do I want to throw away? Okay? And the decision of what to retain, what to throw away is based off of the forget gate. And the forget gate gets two inputs. Basically, the output of the previous state, so ht minus 1 and ht here. So ht minus 1 is the output of the previous cell and the input. And you don't necessarily have to have this connection, and you can play around with this. But so this is what the previous state produced as an output, and this is what the current state receives as an input. Okay? And so based off of those two things for information, I decide what to forget or what to retain in the current cell state. That's what this function here does, okay? All right, so next step. Now we have the input gate. And again, what this does, it takes the previous output and the current input and decides here, in this case, what part of the input is important and what part is not. Okay, so it cancels out or it allows through certain parts of the input. And the computation happens here in the tangent hyperbolicus state, and now from this output I now cancel out or allow through stuff to go in, okay? So this is what happens there. And then the cell state is updated based off of like what I want to forget and what I want to add to it. Okay, so this is basically canceling out or allowing through new information, and then I add this new information to my current cell state. All right, and you already can see that, for example, all of these have the same size, and here as well, because you're computing these pointwise operations. Okay, so these are all like the same size of the like each layer is the same size. All right, and then the last one is the network output, and again based off of the inputs, I decide what of the current cell state I want to produce as my output. Okay, and then my current cell state goes into the next time step, and my current output goes in the next time step. So this is kind of like really step by step how a LSTM works, and so if you kept track of all these kind of functions here, you can imagine like the model, and the model is kind of like sequentially going through all of these, and you have all these types of computations, and the good thing is all of them are differentiable. So you can do arrow back propagation, and you can use Atom as an optimizer and so on. But the main thing is that I don't want to derive the update function or the gradient descent function for this. And so if, like it's pretty complex, and I think we can get away with not going through it piece by piece, but more or less kind of like explaining or like thinking about what are the applications that we can have with these LSTMs. So this is kind of like clear how the process in an LSTM works. And so the idea is that through these sigmoidal gates here, I can retain information over longer periods of time, because I could, for example, learn that most of the time like it should be ones, and then sometimes I just cancel it out as a 0 or something like that. So so these are kind of like the basic like Lego parts or Lego pieces for a long short-term memory neural network. I met the guy who came up with it, Sepp Hochreiter, last year, and he was like, he was actually mostly joking about the fact that this is still going on and they're still using this stuff. They basically meant it more as a, like someone, I forgot who it was, but I think it might have been Benjo, but like I'm not sure. But someone asked them, or said like there's no way to learn these long dependencies in data. And they said, well, challenge accepted. Came up with this thing, and then it was on hiatus for a long time because nobody could train this stuff, and there was not enough data, not enough computational power to actually make something useful out of it. But now we have so many applications for this. So for example, I brought a couple of examples here. I want to talk a little bit more about language modeling later. But so a couple examples here. So automatic image captioning generation, or speech recognition, question answering, and so on. And so for example, one of the ways to evaluate LSTMs would be if you have this image kind of like as the input to the LSTM, and then you want to produce this as the output. So in this case, this image is a baseball guy, like a batter trying to swing at the pitch. So the man at bat readies to swing at the pitch while the umpire looks on. So I honestly don't know if this is a human-generated caption or if it's a machine-generated caption, but it captures the problem perfectly, I would say. Like there's not much more to this than whatever's going on here. And the interesting part here is like, well, it readies to swing, right? I mean, like this is, you can see the dynamic happening in this posture already. So like, it's not just a batter and an umpire at the base, but it's like the process of doing this. And so, how do you learn something like that? Well, you take images. So you take images at your input, and sometimes you would look at patches in the image in sequence, right? And then you produce a word after the other. So the last function that you would generate is kind of like word by word by word. You can also do it by letter or by character separately, but you would train these pairs. And then in this case, here's like a large bus sitting next to a very tall building, and so on. So there's a lot of these kind of examples that you can learn, and there are large data sets where you have image plus caption. You can learn these networks, and they kind of become very impressive. And I'm again not 100% sure if this was like human generated or machine generated. But I also would like to give a couple examples of things that I saw don't really work. And so, for example, here, and like where actually the limitations of these networks are. So in this case, what do you guys see? Well, people shopping at a bazaar. Not so bad. Might actually not be a bazaar. Might be like a different sort of market. But what I think is most striking, and this is actually an example, it's not the exact image, but one of the examples that Benji brought to a keynote that he gave at ICMI in 2015, I think. 15. And basically, and now the networks have gotten a lot better. Basically, my main issue with this is, yes, a human can be fooled by this, and I would say, oh yeah, that's pretty good description of what's going on here, right? But it's actually not. It's kind of like the opposite of what's going on, because it's not people shopping, it's people selling, right? Yeah. So you kind of have the complete opposite. It fools us that, oh yeah, it's pretty good, but it doesn't really, okay? And then the same thing here, a skateboarder trying a trick in a half pipe. Well, it's a half pipe, and someone's trying a trick, but he's not the skateboarder, right?
Get a bike.
He's on a bike. So, what does this tell us? This tells us a couple of things. So, if you remember these embedding spaces that I showed you, where you have the word auto, and then you have all these images of autos around it, right? And so you can turn this around and say, like, okay, I wanna jump to a location where I have an image that looks very similar to this image, right? And so large parts of the image are very, very close in some cases. So if you would change this image to a skateboarder trying a trick, what part of the image would you have to change? Well, you would change this part here, right? And maybe this part down here, but this is pretty minor and pretty small. And then you have the same image, right? So what I suspect happened is that there were not many BMX riders in half pipes in the training data set. But there were quite a few skateboarders in the training set. And now what the algorithm does, it looks at the new image, that is this image, and compares it, okay, where in the space does that fit? And it fits here, like, what's my nearest neighbor? My nearest neighbor is somebody doing a trick with a skateboard, and then that was the sentence that I have to produce. That was exactly that sentence, right? So, it is not quite clear if these image captions, like if you do it in a naive way, are getting much, much better results than if you would just do nearest neighbor. Like, just spit out the nearest neighbor location of one of these images. Okay, so some more modern algorithms that can deal with this are also modeling attention. So they actually pay attention to like sub-locations in the image more than others, so that they can actually learn more like fine-grained changes in the image. Okay, and then you can then also utilize their attention output as like a comparison of like, how did they come up with this sentence here? Was it just because of a nearest neighbor, or was it because of like a certain the network's ability to pay attention to the right part of the image? Another more complicated or more difficult task here would be the visual question answering, and I think we can actually try this out. Is there a demo? I thought there was a demo. Okay, there is no demo. Or I don't see it right now. Oh no, here is a demo. Alright, so let's try this. Okay, so click on one of these images to send it to our servers, or upload your own image. Which one do you guys want?
The tennis.
Tennis player?
Yeah.
Okay, let's click on that. Alright. So, what question do we want to ask?
What happened?
What happens next? Okay. Here we see how well this works.
Will he hit the ball?
Will he hit the ball?
Or is that too?
It's too simple.
Yeah,
Yes.
Okay.
Yeah.
not bad.
Competencies.
What is happening?
Yeah, what is happening?
Tennis.
Oh, wow.
Who is he? Will that work?
I don't
No,
think
they
so.
don't have that.
Who is the player? Man,
Wow.
not bad.
That's bad.
what is at the top edge of the image? Ball.
Oh, wow. Okay, I see that, yeah.
So, what is the background? Shadow, trees, not that great. Tennis court, I was asking.
What's in his hand? No, I'm sorry.
What's on his head?
What is on the player's head? Okay, so this could be, by the way, like this could be, you know, motivated also through the fact that like the verbal or the word embeddings might actually be more like informative to give you that answer than the image itself. So that's also possible. So it learns from both sides, right? Like it learns from typical answers, but also from the images that correspond to this. Okay, so this is kind of one of the things that these.
Will it work on like a question fragment, like color of court, instead of what is the color of the court?
Blue.
Oh, okay.
But yeah, so this is kind of
Okay. That's right, another one.
some of the things that these networks can do. All right. All right. So visual QA, I think, is something interesting, something cool to look at. I would like to now also go into a couple of more examples. And this goes back to your like translation question that we had. So in traditional non-recurrent neural networks, we basically have an input, we go through a network, and we produce an output. So that's kind of like our multi-layer perceptron kind of approach. In this case, one-to-many, we would produce, or we would like give one input and then produce a sequence of outputs. And you can see here that the network state, again, is propagated through time, and then an output is produced at each step. So that would be one of the ones that we just had before, where we generate a caption to a single image as input, okay? Then you can also consider this, for example, where you have multiple inputs in sequence, where the state of the cell is propagated through time, and then we produce one output at the end. So that would be, for example, like emotion recognition of a sentence, or sentiment analysis of a sentence, and so on. And then we have other cases, and I would do this one before this one, but anyways, so you have multiple options of many-to-many connections, where in this case you would produce a couple of inputs first, and then you would produce outputs at towards the end. So you want to kind of like learn a sequence to another sequence. So this is typically used for machine translation, where in this case you kind of want to have the information of the entire sentence first before you translate it. You don't want to do it word by word to translate. For example, you want to have the complete context, because like if you translate, I don't know, German to English, you don't translate word for word, because that would be like how Google Translate worked, I don't know, 7 years ago or 10 years ago, right? So that sounds awful. But now it takes the entire sentence into account, and then tries to generate, based off of the current cell state, the outputs respectively. And then you can also think of many-to-many applications, where each input produces an output at the same time. So this is our synchronized outputs. And one of these, for example, would be a language model, where you try to predict, based off of the current word that comes in, the next word. Okay? And we're going to have a couple of examples here that we can look at. And so here is one of our sequence-to-sequence, many-to-many language models. In this case, the language model has 4 outputs, and it's H, E, L, and O. Okay, and it has also the same number of inputs. In this case, it's a one-hot vector for each of the words that are legal in the grammar. Okay, or in the language. And so the first one comes in. It's an H. The hidden state gets updated, and we produce an output, and we have the highest value. No, we actually don't. We have the highest value at the O, but the correct output in this case will be the E. So we produce from the H as input the output, the target E, and then we propagate the cell state further, gets multiplied and added to, and then we have another input. We have E as an input now, and we want to produce the output L, and now we have L as the next input, and we produce in total, in sequence, we try to produce the word hello. Okay, and so obviously, like in this case, sometimes the outputs were incorrect, so this would be the output because it takes the one that has the highest support, and in this case it would be the O, and so on. But this is like how you would train this network to learn to produce the word hello, for example, or other words that you can create based off of these 4 words. So for example, if you start off with an O here, it could generate maybe the word ole or something like that, or yeah, or whole, something like that. So that's kind of so yeah. For example, H, O would already go into the direction of whole, and so on. So you can imagine this as one of the examples here. So how do you train this? Well, you train it basically in a similar fashion as we showed before with the skipgram for the word embeddings. But what you do is you basically have an input string that is so you have your input, which is a sequence of targets. Okay, and these are basically our and you only have you only have 4, and we have a target sequence that has the same length because we do sequence to sequence learning here, and basically that one is just shifted by 1. Okay, this is literally how you train this. You try to use whatever comes in here to predict that, and every time step you kind of produce an error or you produce a loss, and you use that to update your network connections. And so, excuse me. So you try to predict based off of the input what the next step is, and then you have the next step as your input. Okay, so this is like how you prepare your batches as like training and target signals. And you basically take your input and then shift it by 1, and that's your target. And so like that's kind of like how you learn these things in TensorFlow, for example, or Keras. All right. So what is
Sorry, so quick question. So afterwards, after the model has been trained, every time when you say, for example, HELL, it will predict the next one for sure as O.
Yeah, I mean if you overfit it, yeah.
Okay.
Definitely. It's not guaranteed. The beauty of these networks, and you will see that in a second, is that they're kind of stochastic. So you don't necessarily always produce the same outputs. Like it's different from a nearest neighbor learning, where you would always, with the same input, you always produce the same output, right? But because there are some stochastics that you can put on top of this, or there are some stochastics with like how the initialization goes and so on, that you could generate different outputs. So one example, for example, is like at the output, you're very unlikely to get like a very clear distribution of what word you're gonna, or what character you're gonna produce next. but you're more getting like a distribution. Like there are many zeros in the distribution, so you definitely not want to produce anything that has like very little probability to be produced. But then you get a distribution at the output, and you can choose based off the distribution what you're going to do next, right? And so that could influence like where your sentence goes afterwards. And I'll show you this a little later in an example that we just published, where we tried to generate affective text, or like text with emotion. Okay, so this is kind of like the basic step, like how this looks like and what they produce. I would like to show a couple of examples, and so for example, this one is trained on Paul Graham essays, which are these here. So basically, one of them is Life is Short, from January 2016. Having kids showed me how to convert a continuous quality time into discrete quantities. You only get 52 weekends with your 2-year-old. If Christmas as magic and so on. So this is kind of like how the person writes. And what the idea was to learn basically the style of this person and reproduce a essay or like part of an essay automatically. And in this case, it used like 1 million characters, which is relatively small. So the input of the training material is only 1 megabyte. So this is kind of like what it produced. So thus surprised in investors weren't going to raise money. I'm not the company with the time. They're all interesting quickly. Don't have to get off the same programmers. There's a super angel or angle. Super angle. Round fundraising.
I think it's Angel.
Angel, right? No, it's Angel, right? Yeah. So there's some kind of connections with like investors weren't going to raise money, and there's like some investors' money and angel round funding and so on. But like it's not really correct-ish, right? So it was trained on a very small data set. So this is kind of like one example of like how this can look like. Another example is to train a network on all that Shakespeare has written, and then it produces stuff like this. So alas, I think he shall become approached, and the day when the little swain would be attained into being never fed, and who is but a chain and subjects of his death, I should not sleep. Not trying to explain what this means, but yeah, so you can kind of guess, like, it gets sort of like the idea of some old English words like alas and stuff like that is in there, but it kind of produces gibberish in a sense, like if you look very closely, okay? But so this is learned on 4.5 million characters, and so I would like to take a few minutes now to basically introduce one of ours that we trained, and we call this one the affect LM, so the language model that can produce emotional sentences. And so what we trained it on is this first data set here, the Fisher data set, which contains 11,000 conversations, about 10 minutes each. And we have now about, so it's like 3, so we have 21 million words in our data set, okay? So instead of 4 million characters, we have 20 million words. So that's a lot more data than they used to generate Shakespeare. But here are a couple of problems that we have. So first of all, this is not proper grammar. People talk in these cases, and it's like conversational data. There are repetitions in there, so like I don't know. right, and stuff like that. And so people are talking to each other, and it's a pretty large data set. It's like, I think 2,000 or 3,000 hours of data, something like that. So it's a lot of data that we had, and we wanted to learn a network that is able to produce conversational language or conversational text. And I have a couple of examples. But we didn't just want to be able to do that, but we wanted to do the following. So we wanted to take a couple of context words as input, and then kind of complete whatever would be produced afterwards. But then we wanted to be able to kind of tune that. We wanted to have like these tunable parameters. In this case, we wanted to say, well, I want to complete this sentence, but I want to complete it happy, angry, sad, surprised, or whatever, or like just neutral. And I want to have this affect category to be influenced by like an affective strength as well. So I wanna make sure, like, if I have a happy context that I want to produce, or like a happy ending that I want to produce, and I want it to be super happy, I would crank that beta up as well, right? So with a low beta but with a happy context, you would get, I feel so good about this. Then you crank it up a little bit, the emotional strength, and you get, I feel so great about this. And then if you crank it all the way up, he's like, I feel so awesome about this, okay? So this is kind of like what we wanted to do. We wanted to change this kind of word that pertains to the affect strength. And if you wanted to tune this to like negative, so you would put it to angry, for example, now you would produce something like, I feel so bad about this, okay? And super bad is like, I feel so horribly angry about this, okay, something like that, okay? So this was the idea. And well, how do we do that? Well, we need to both learn the language, so we have the language model learn what to produce as the next word, but then also we wanted to tell the language model what context it is in right now. So we wanted to tell it, oh, this is a happy context, this is a sad context, this is an angry context, okay? And we since these are all unlabeled data sets or unlabeled conversations, we don't really know what the context is at any given time, right? So we had to infer it some way. So we had to automatically infer the context of the conversation. What we used is the so-called language inquiry and word count dictionary by James Pennebaker. That basically is just a long list of words, and all of these words have category labels. So for example, there is the word bad in there, and it has the category label like negative affect. It's an affective word, so it has the general label affect. It has a negative affect, and it has like maybe an angry word or something like that, angry category as well. And then there's happy, that has a positive affect category label, and yeah, a happy category label or something like that. Okay, so this is kind of like it's just a list of words with different contexts of happy and or different labels like angry, happy, sad. So this is kind of like what we're using to train this model. So we tell the model in what context it is in, and we try to learn the distributions and the words that are being produced in different contexts separately, okay? And then we evaluate our model in the traditional way, which is basically how good are we at predicting next words. So that's kind of like what you would test your typical language model with. But then also we wanted to make sure that people think that our sentences are meaningful, that like this we did on MTurk. We wanted to have people rated on grammatical correctness or naturalness and so on. And then we also wanted to make sure that whatever category we choose here to generate the next sentence, we wanted to make sure that the people recognize that now we changed the affective context. Okay, so what we would do is we have the same starting sentence, but then we change the affect category. We wanted to hear if people think that we produced sentences in different affect contexts. So I brought a couple examples. So we have the same starting sentence, I feel so, and then we wanted to have this happy, okay? So what's happening, so we say the context is I feel so, and we say, but now we're happy, and then the model completes the sentence like this. I feel so good because I think it's important to have a relationship with a friend. Sounds like happy, or sounds good in a sense, or positive emotion. And then for angry, I feel so bad that I hate it. I hate it that they kill themselves and they fight. So like, yeah, obviously sometimes a bit gibberish, but we told people it's from a conversational context. It's not really meaningful to like judge it on just repeats and like I miss the feeling of family members and so on. So this is possible in language, like people do these repetitions all the time. But again, also now we see that the context changes, and like there's sad, there's missing something, for anxious, horrible, and there's like words like alert, actually gonna die and stuff like that. So it's like kind of these feelings of anxiety and stuff that is happening, okay? So something is going on, all right? And then if you have a feel so and the neutral, this mostly picks the words or the context where this happens to be the predominant frequency. So with these contexts, we change the frequency, we change the production of words, but the neutral one is what the language model without the affective context would produce. So this one, I feel so bad. So that's the same example as with the hello example. The more often you have the word hello in there with a starting H, you would always predict E as the next character and so on. So this is produced based off of the most frequent words. All right. Okay. So and now how did we evaluate it? So we had we generated about 200 sentences in each affective category. So that we had like 5 affective categories. We produced it in 200 sentences for each of them. So that's like 1,000, and then we had the different beta values, which are either 0, which is the neutral case. So 0 beta means 0 affective strength, that creates like neutral sentences. And then we cranked it up to 5. And we wanted to see, for example, in this case, do people recognize that with increasing beta, that the affect now is happy, or the affect valence goes up? And we do see a change here, and we actually see that people recognize significantly more that happy and positive affect is happening with a beta strength of 3. For negative emotions, it's not that precise, because negative emotion actually was subdivided into angry, sad, and anxious. For angry, we can't really separate out the difference between angry, sad, and anxious, so it was not super clear cut out. So that also means that oftentimes in our data set there might not be that much anger. It's more sadness, for example, is very clearly cut out in our data set, so people talk about sad examples. And then also anxious kind of was predicted appropriately. So this is kind of like the way we evaluate this. Then we evaluated for each of the emotions if the grammatical correctness falls significantly. And what we see is that the grammatical correctness seems to be stable until like a beta of 3 is arrived, or is reached. And then after that it drops dramatically. And for example, for anxiety and sad, that means, for example, if you crank that beta value up too high, the words that are sad or anxious sounding will be just repeated all the time, like alert, 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 and so that doesn't make any sense in grammar anymore, so people would recognize that fairly quickly. But another really interesting additional benefit of our model is also that in typical language modeling, you try to predict what the next word is going to be, and you measure how accurate you are with the so-called value of like perplexity, which is basically 2 to the power of the entropy of the distribution. And so you want that to be as small as possible. You don't want that value to be very high. And what we found is that while it was not very significant improvement in our data set that we learned, we found that there is quite significant improvement in our other data sets. For example, our depression interview corpus, in our emotion data set, in a movie opinion data set, where emotional words are much more frequent. So with the affect LM, our model, you can actually better predict what the next word is going to be if your data set is pretty emotional, right? So if it's very neutral, you're not gaining from the additional information about the affect in the text or the sentiment in the text. But if it's very emotional, you actually gain quite a bit of improvement, and we were really excited about that. And like one of the ways this is happening, and again, we have a Tisney representation here. One of the ways this is happening is because our embedding space now learns regions of words that are happening often to be close to words that are like in a positive emotion, like why is exciting, glad, anger, hate, stupid, dumb, damn, lies, and so on. And now, like there are a lot of gray words also close to these negative or positive words, and because we learned this distributional hypothesis of emotion or affect in text, and the Luke words in the dictionary, we learned that there's kind of like this gradient from happy to sad words over neutral words, so that the big bulk of words is neutral words. But words that are actually gray up here and close to this happy cluster, or gray that very close to the anger cluster, those are words that are not in the Luke dictionary, but are close to words in the Luke dictionary. And so that means that these words should actually be related to the Luke categories, which are happy, angry, sad, and so on, but are not in the dictionary itself, but they are present enough times in close vicinity to the words that are in the dictionary, which are not that many. This dictionary is not very large. And so that would basically help us to better refine or better collect a larger and larger dictionary with affect-related words. So just through this, we can learn this as well. So this is kind of like one nice side effect. So for example, some gray words that are happening close to anger were war and terrorism, and they're not in the dictionary itself, but they are related to anger. So that's kind of one of the interesting findings that we had there. All right, so that's it for today. Are there questions?
Did it generate like sarcasm or that?
We would love to do that. That would be very interesting. I don't really have a sarcasm data set that we could learn off of, but I would love to try something like that. Or irony, or you know, maybe even like being able to make jokes, something like that. But yeah, so you can generate a whole bunch of these different things with these models.
So, question, for the initial value of the starting point, like, does it really matter? Because you mentioned it can be like either randomized or just like start zero.
Yeah, I think it might matter, but I don't think it's a big deal. Did you try multiple ways, or?
No, I'm just curious.
I would start it with like a little random, like I don't know, just like, but not very high values. Like down, like maybe take a normal distribution, mean 0, 1 standard deviation, and then like multiply it by 0.1 or something like that, so that the It's low, not too high, but maybe not all zeros.
What was the quiz on? Is it from like kernel?
Yeah, so it's basically from the last quiz to
Yeah.
support language, I think.
Yeah.
What was it?
Was it multimodal?
Like before.
Before multimodal.
Before.
Oh, before multimodal.
Yeah, I think it's before multimodal. Yeah, before multimodal. And we have the multimodal for the finals.
Is the final gonna be like?
I think it goes.
Because I don't see like any
It goes up
dates
to.
on mine.
I don't know, like they always tell me very late.
Oh, really?
Yeah.
Yeah.
The last time I waited until like 4 days before it. And
Oh, really?
Yeah, so it's,
I think, yeah.
But it's gonna be sometime during
early May.
Early May, okay.
And I had like people already booked their flights and stuff like that. It's like, what?
Oh, okay, why slide up?
Cause I thought we were gonna take it during the last week at first. The first week of May works better.
I mean, we can do that. But I think the official day will be then, because there's the learning
Yeah,
week as well.
yeah, I think that works better for me anyway.
Yeah, so the official way is to do it that way, but in general, we could do it like a midterm, just during class, but, yeah.
So does that mean we don't have a final, like, actual exam?
Yeah, we do.
We'll have a one after this upcoming quiz, right?
Yeah, and after the semester is over. There's like, the semester is over, then I think there's a learning week,
Yes.
and then it's in that week after that.
Which is like the first week, almost like the first week of May, right?
Yeah, but I don't know when and where.
Okay.
They will tell me.
Also for the project,
Wait, I
paper
have
you
this
mentioned,
in
like,
my.
should we start drafting it right now? Or like we can just expand?
No, expand your,
Sorry.
yeah.
Monday.
And that one will be due,
Well, I didn't see anything like that.
On the scheduled classes.
Oh, really?
I can double check those. Is it on the
but
8th?
isn't that, there's a
Oh, they just
quiz
show.
on this Wednesday?
Yeah, so there's a quiz this Wednesday, but this was the final exam.
Oh,
Yeah.
okay, so, okay, so still have some like.
That's
Yeah.
it's one day before and I'm pretty fine.
Dude, I feel you. I have an infectious diseases exam like the next day.